Thank you for joining us for today's webinar, FRP Strengthening Concrete Structures with Fiber-Reinforced Polymers. We're excited because this is our first joint US and Canada webinar, and we'll hope that it'll be the first of many. It's also AIA certified, so if you haven't already submitted your information, please do so. Now, we have some brief housekeeping before we start. Your phones are on mute. If you have any questions, please type them into the Q&A box in the corner of your screen, and we'll answer them at the end of today's session, time permitting, or via email after. And you can always send questions to mapeidigital@mapei.com. Now, without further delay, I'd like to introduce today's speakers, Brian Stratman and Hamza Uzia. Brian is the Business Development Leader for Corrosion and Structural Strengthening with Mapei Corporation. Brian's work experience includes structural design of commercial and retail structures, territory sales manager for power and industrial concrete repairs and grouting, business development manager for steel piling. Fiber reinforced polymer, FRP, strengthening and corrosion mitigation. In his current role, Brian is responsible for business development and engineering support related to Mapei's structural strengthening and corrosion product lines. As a PE, he has over a decade of experience related to the design and installation of FRP strengthening systems for concrete and masonry structures, and is also a NACE certified cathodic protection technician, CP2. Brian's also an active member of the ACI 440 Strengthening Committee and ICRI Strengthening and Corrosion Committees. Hamza Uzia is a sales engineer for Mapei Canada. He holds bachelor's and master's degrees in civil engineering from Polytechnic School of Montreal. He provides support to engineers, architects, and owners for the specification and field support of Mapei products and systems related to concrete, structural strengthening, repairs, injection solutions, industrial flooring, waterproofing, and underground construction. As a certified Mapei Technical Institute, MTI, instructor, he provides theoretical and practical training to engineers, architects, and installers. Hamza is also a member of Construction Specifications Canada, the American Concrete Institute Quebec, and East Ontario Chapter, and the International Concrete Repair Institute, for whom he received 2019's 40 Under 40 Award. Brian, Hamza, the floor is yours.
Okay, well, good afternoon, good morning, I guess wherever you might find yourself, but I hope everyone's doing well today. We'll jump right into this here. So let's see, why is this not, there we go. Okay, all right, so we're going to be talking about FRP systems today, fiber reinforced polymers. We have really four kind of main objectives. The first to just be a basic understanding of what these materials are, their structural behavior, as far as how they interact with the concrete, etc. Then we'll talk a little bit about the various applications that FRP systems are appropriate for as it pertains to concrete. We'll only be talking about concrete today. We're not really going to get into masonry too much. It's mostly just concrete that we're talking about, but you can use these for masonry as well and some timber applications also. But today we're just going to be talking about concrete. Then we'll learn where it's appropriate to use these systems, as be flexural strengthening of beams, walls, etc. We'll kind of go through the different applications. And then Hamza will come on and walk you through some of the installation issues, quality control, things like that. So with that, I will jump right into it. So really, when we're talking about FRP, we're talking about strengthening typically. Sometimes we use it for protection, but mainly we're talking about strengthening of existing structures. So there's really four kind of main reasons why we would be looking to strengthen a structure. The first is simply looking to increase the load-bearing capacity of that structure. So that could be due to a change in use. So maybe you have you know, an old warehouse that's being turned into apartments, and you need to increase the live load ratings for the floor. Could be, you know, maybe you have an existing office building and they want to, you know, put a, you know, maybe it's a law office and they want to put a library of books. So then you have that big heavy load that you need to account for. So you might have those new load conditions. And then of course you could have design or construction errors. So either, you know, the engineer possibly, you know, under designed, which certainly happens from time to time, or there was a construction error. The bars were supposed to be at, you know, say, you know, 12 inches on center, 20, you know, 25 centimeters on center. And they got put at say, you know, 16 or 18 inches on center, or, you know, just 10 centimeters on center as opposed to the 12 or 25 that we were looking for. So obviously you have to come back in after the fact and fix that. So that's one of the big reasons that we get involved with FRP. And then the second one there, certainly the biggest, we say damage or deterioration. Really, that covers a lot of different things, but mainly we're talking about corrosion. Obviously, corrosion is detrimental to the strength of the reinforcing steel as it corrodes and loses section area of the steel. You lose some of that flexural capacity or shear capacity, whatever application you're dealing with. So we need to get in and replace that strength that's been lost. So certainly, probably one of the more common reasons we'd be using FRP. But then beyond just corrosion, you could have cut or damaged reinforcing steel. So, you know, oftentimes if they're, you know, maybe a new tenant's moving in, they want to cut some new holes in the walls or the slabs for, you know, HVAC systems or running electrical wiring, whatever it may be. They'll cut through the wall or the slab, the beam, whatever it may be, and they'll damage that reinforcing steel while they do it. So you got to come back in and replace that damaged steel. Impact damage, this is generally trucks driving down the highway and they hit the bridge. Happens a lot more than you probably would realize, but you know, either they have a load that's too high, or you know, it's a low clearance bridge and they weren't paying attention. They just are driving along and they clip the bridge. And if there's damage, then you obviously would need to get back in and fix that. And then you could have fire, earthquakes are certainly a big one. FRP is great for seismic strengthening, which kind of gets into that third bullet point, so increasing seismic performance of a structure. That's where FRP was first used. Actually, in Japan was the first commercial use of FRP, and it was to increase the confinement of their columns after a big earthquake exposed the fact that many of their columns were under designed for the size earthquakes that they would be getting. So the last one there, blast resistance, really doesn't come up super often, but it's, you know, it's obviously a very specialized kind of engineering application, but FRP materials are very effective to increase the blast resistance of structures, and certainly can be used if you have an application that would require it. Traditionally, when we strengthen structures, there's certainly many different ways, but some of the more common ones, bonded steel plates, where you either just use epoxy to bond the plate, or you can see in this picture on the lower left there, they bolted it into the slab. Then there's external post tensioning that you see there on the right, where they actually put external PT cables after the fact. The issue with kind of some of these more traditional strengthening techniques is one, they're very heavy if you're talking about steel plates, so you need a lot of big heavy equipment to get them installed. But the bigger issue is really that you're almost always having to penetrate the concrete, either to put the anchor bolts in or you know, just to fasten it in place. There's different reasons, but anytime that you have to start, you know, penetrating or drilling into the concrete, there's a pretty good chance that you're going to damage the existing reinforcing steel, which of course is just going to compound whatever problem you're already trying to fix. So if we can avoid that, then that would certainly be advantageous to do so. With concrete, another real common way to do it is just simple section enlargement. But again, I mean, you can see here they're making, you know, dozens and dozens of penetrations. You're also losing, you know, if you're in a parking garage, generally speaking, you don't have, you know, even an inch or two of overhead space to spare. So if you have to lower the beam, you know, by enlarging it down, that's just simply not possible oftentimes. or even in an office building or somewhere, it may be possible, but in general, the architects are not trying to give up much of their floor space if they can avoid it. So it's not necessarily the most desirable outcome that you might be looking for. Now with FRP systems, you really solve all of these issues. It's very, very low profile. Generally, the installed thickness is going to be less than about a 1/16 of an inch, which is, I don't even a thousandth of a centimeter or something. Very, very thin. Very, very, very thin. Easily concealed with top coat. So the picture we're looking at here is a kind of a before and after. So you can hide it. I'm not going to lie to you. If you were to go, and this is actually the Alabama Crimson Tide football stadium. So if you were to go to an Alabama football game and find this column and walk right up to it, you're going to see the fibers through the coating. If you're looking for them, but if you're just kind of walking by casually, not really paying much attention, you're not going to notice it all. So it's very, very concealable to the general public. Minimal equipment. Everything you need really can be held in your hand. The surface prep equipment would be the largest. If you're doing obviously sandblasting or something like that, you're going to have some larger machinery. But oftentimes they're just using angle grinders and such, and Hamza will touch on that later. So really no big heavy machinery required. A man lift, if you need to get elevated, but the actual tools themselves will fit in a small tool bag. So it's really, really convenient from that perspective. And then the big item, it doesn't add, because this material it's not weightless, but it's very, very, very light. So you're really not adding any kind of appreciable dead load to the structure. So if we were to have done section enlargement with this column and we're on a supported floor, now you've got to look, okay, well, I'm adding, an extra, say, 6 inches or, 30 millimeters, whatever it may be, of concrete around that column. Is all that extra weight going to affect the ability of the slab or the beam that's supporting the column from below? Is it able to carry that additional weight? If it's just one column, probably yes. But if we're talking about doing this on, a whole parking structure, for example, all that cumulative weight really starts to add up, and then perhaps your foundations might not be able to carry that load. So with FRP, you just eliminate all of those potential issues. So I keep saying FRP. FRP stands for fiber reinforced polymers. So what that is in the basic sense is you have some type of a fiber, and then those fibers are encapsulated in some sort of a polymer. In our case, this is an epoxy. The picture on the right that we're looking at is a magnified view of an FRP sheet. Little round, kind of spherical looking things you see in the picture there are the actual individual fibers. So those get bundled up. If you've ever seen an actual sheet of FRP, there's little bundles of fibers, and then those get woven together. So what we're looking at here is one individual fiber of that bundle. It's about 1/20th the size of a human hair as far as the diameter of it. So it's very, 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 very small. But as you'll see here shortly, it's very, very, very strong at the same time. The types of fibers that you'll see used in the strengthening market for concrete, carbon is going to be used probably 80–90% of the time. Really, anytime you have a true strengthening application where it's under sustained load, you're going to want to use carbon. I'll get into that a little more here in a second, but the glass fibers are generally more applicable to something like a seismic event or just simple, protection. Like, kind of a lot of the DOTs will just wrap columns. If they're out doing work on other parts of a bridge, they'll just wrap the columns just to kind of give it some kind of belt and suspenders protection. So you're not really loading it per se. It's just kind of there to hold everything in place. So we'll talk more about why that is here in the next couple of slides, but just keep that in mind. And then the last one there, Aramid, most of you probably more familiar with Kevlar from bulletproof vests. There are some manufacturers that sell Aramid fibers. We're not one of them. This material is incredibly tough. I mean, there's a reason it's used for bulletproof vests. I mean, just cutting a sheet that's 40 centimeters wide or say 16 inches wide, I mean, you're going to spend a good 5 minutes just trying to cut, with the pair of scissors to cut through it because it's just so tough, the fibers. But really, you'd only use it for like a blast application, just general flexural or shear strengthening. You wouldn't want to mess with the Kevlar. One, it's very, very expensive, and then two, it's not very user friendly. However, if you're doing, like a really high, large blast strengthening project, I mean, it certainly would be something worth looking into. So I mentioned we'll get into the kind of the benefits of the carbon, and so that's what we're going to do now. Carbon is very, very high strength and very high stiffness, much more so than the glass, which is also very strong, but just not quite as strong as the carbon. And it has excellent durability and endurance characteristics. So when we put it through, cyclic load testing, when we, do environmental exposures to chlorides and things like that, carbon really holds up much, much better than glass. And also is not very susceptible to creep, whereas glass is very, very susceptible to creep. So because of that, if we're doing a flexural strengthening, shear strengthening, any type of load where it's going to be constantly loading the FRP, you're going to want to use carbon for that, with the one exception of the material is technically a metal. It's not a metal, but it is on the periodic table. It certainly exhibits properties of a metal, and because of that, it is conductive. So if you're in a say a mechanical room and you have a concern with sparks or something like that, there certainly is a fire hazard with carbon. And then also the big thing to pay attention to is because it is conductive, if you put carbon directly in contact with steel, it's actually going to make the steel corrode because of dissimilar metals and the lower nobility of the carbon versus the steel makes the steel corrode just being in contact with a different metal. So we do different things to insulate and make sure that contact doesn't happen, but something certainly to pay attention to if you are going to have any contact. This happens a lot if they're having to hang a steel plate for some reason, after maybe there was a drop tile ceiling or something, and they have to install the little hanger rods for the ceiling, or a plate on a beam, any number of different reasons. But if you do have metal in contact with the carbon, that's something we need to be aware of so we can address. And it is very easily addressed. You can insulate it with the epoxy. It's just something that you do have to pay attention to. For the glass, again, it's also very, very high strength, especially for its weight. But it's about half as strong as the carbon. But the big thing with the glass is it's non-conductive, so we can use it as an insulating layer in those situations that I just described if we need to. It gets used primarily for single events like a seismic event, an earthquake, where it's just going to take the load, and then after the event, you can go and inspect it, see if it's damaged at all, if it needs to be repaired before it gets another earthquake. The reason for that is glass is susceptible to creep rupture. So as it's placed under constant load, it really starts to stretch and ultimately will rupture much more rapidly and prematurely than you would see from the carbon. So it's just really not ideal. It doesn't have that durability and endurance that the carbon has. So we try to avoid it for flexural or shear strengthening, where it's just under constant load. The difference, or the exception, I guess, the exception to that kind of rule would be for masonry, which we're really not talking much about today. But because masonry is much lower strength than the carbon, sometimes putting carbon, it's actually too much stiffness for a masonry wall. So you would go and use the glass in that situation, just because it provides a closer amount of capacity to what's already there. You just have to apply more severe durability reduction factors to it that both the CSA S806 code and the ACI 440 code both address that when you're designing. For the polymers that we're using to encapsulate these fibers, there's literally thousands of different polymers, but all the FRP manufacturers are using epoxy. We use epoxy because it's got very similar properties to the concrete as far as the stiffness and the flexural capacities and things like that. It just lines up the best. It also adheres exceptionally well to the concrete. Of course, the one downside to that is epoxy has absolutely horrible fire endurance. So you're going to lose the FRP system when it's exposed to a fire. And we'll get into that a little bit later on here. So just kind of comparing some of the different products. So I put some of the more traditional weights of fabric that you'll see. All the FRP products in the market are designated by a weight. The two most common that you'll run into are 9-ounce or an 18-ounce carbon, which is 300 grams a square meter or 600 grams per square meter. More recently, we've seen some heavier fabrics coming out. We have one as well. These are, I've got a typo there, I apologize. It should be 1,200 grams per square meter on the third column and 36 ounces per square yard. So essentially that's 4 layers of the lightest one on the left hand, but it's all combined into one layer. So you will see those used here and there, but you really can't double up the layers too much. You're probably limited to, 1 at best 2 layers of that really heavy weight. The 36 ounce or the 1,200 grams per square meter. The glass typically weighs around 900 grams a square meter to 27 ounces per square yard. But you can see kind of the design thicknesses, are very, very, very low profile, very thin, 200ths of an inch. This is the cured thickness with the epoxy. So, half a millimeter, 2 millimeters, we're not talking much thickness at all. But when you look at those strengths that we're seeing, the tensile strength, around 1,500 megapascals, around 210 or so kips per square inch for most of the carbons, and in the glass, again, is much less strong, less strength than the carbon, but still pretty good, considering it's only 0.07 or 2 millimeters thick. The stiffness is really the governing property. However, the tensile strengths, everybody reports the tensile strength. It's part of the 3039 ASTM 3039 reporting requirements, but the tensile strength is really irrelevant when we're designing all of the design codes, be it the ACI or the CSA design guidelines. Everything's based off of stiffness, and we'll see why that is a little bit later here. But the stiffness is very, very good, obviously, for all the products. And you can see those rupture strains down there too as well, which have a big part in the design of these systems. Just don't want to spend a lot of time here. Just the one thing to point out, this is obviously a stress strain diagram. The important takeaway from this is that these materials are linear elastic right up until failure. So it's not like steel where you've got your yield point and it kind of tops out and then starts yielding and then it starts reducing a little bit until you get to your failure point. With FRP materials, they're just going to keep taking load, and then all of a sudden you're going to get a sudden failure of it as far as tensile strength. Now, we never are able to achieve the ultimate tensile strength of the material, and I'll explain why that is here in a few slides. But just that's why the ultimate tensile strength is really not all that important, because we'll never get there. It's going to delaminate before that happens. So it's just just to point out the difference between steel and FRP is that it is linear elastic all the way up until its failure point. So there's 3 different types of FRP systems: fabric, pre-cured laminates, and then FRP bars. So the fabric is what we're just looking at on the picture on the top right there. You can see it comes in a roll. These are flexible sheets of either carbon or glass or the aramid fibers, the Kevlar as well. Then they come in uniaxial or bidirectional. There's also a quadriaxial fabric that we carry. I don't think we really sell it here in North America, but over in Europe, they use a lot of these quadriaxial materials for some of these really old, 14th century churches and castles, things like that, they're just trying to do what they can. But when we say uniaxial, the fibers run the length of the sheet. So there's that ruler on the picture in the top right. the fibers are running parallel with that ruler, so it just runs along the length of the sheet. With the biaxial, bidirectional fabrics, they'll either be running at plus or minus 45 degrees, so they, be at an angle, or some of them are 0, 90. It really just depends on the manufacturer. They'll specify whether it's 0 or 90 or plus or minus 45 degree fabric. But the actual fabric FRP products are used. Well, they can be used for any strengthening scenario that you run into, but they're particularly beneficial for column wraps or shear U wraps around a beam. Anytime you have to turn a corner or make a 90-degree bend with the material, you're going to have to use the fabric, because the pre-cured laminates, the plates, while they come in a roll like you see there in the middle picture, they're not going to hold a 90-degree corner and stay bonded. That would be impossible. It's just, there's no way. So we would only be able to use the plates on a flat application. So think slabs, flexural strengthening of a beam, certainly walls, shear walls. It's great for CMU applications because it's a lot easier to deal with the coursing joints between each brick. As opposed to with the fabric, you'd have to try and work it into that, to the joint all the time. It's just be a nightmare to try and install that. So the laminate plates are great for the CMU walls and really any flat application that you may have. It's just a lot quicker and easier to install, as Hamza will describe later. Then there's the FRP bars. These are carbon or glass typically. We'll apply these by cutting a shallow groove into the concrete and what we call near surface mounted application, where you imagine if you have say a parking garage and you got a negative moment issue right in the drive lane. Well, we can't put a plate or a strip of fabric on the top of the concrete where cars are going to be driving over it. Obviously, that's going to damage the system. So with the bar, you can actually cut a small groove into the concrete and kind of internally reinforce the concrete, so you're protecting the FRP from pedestrian or vehicular traffic. So now we'll get into some of the design stuff. First thing you need to do if you're looking at using FRP is to check the strengthening limits. I mentioned the fire issues with FRP. Because you can't fireproof FRP materials, you have to make sure there's a baseline capacity that you can meet. So in the 440, the CSA doesn't have a direct equivalent equation to this, but in the next slide, they do have a statement that for fire applications, that's basically the same thing. But it's basically essentially saying that the existing structure without any strengthening has to be able to carry the service loads on its own. And then if it meets that, but it simply can't meet the 1.2 and the 1.6 safety factor loads, ultimate loads, then that's what we're using the FRP for, is to get you from the service load up to the ultimate loads. If you can't provide service loads with the existing structure and you're going to be relying on whatever system you use to strengthen it, you actually cannot use FRP. And that is particularly true in fire situations. So when you're dealing with fire, there's actually a separate equation in 440 where it's just 100% of the service load. If you don't have fire issues, they give you a little more flexibility, but if you have a fire rating that needs to be maintained, then this is the equation that you need to adhere to. In the CSA, they don't have an equation, but it has the statement that you can read there: original assembly must be capable of supporting the full specified gravity load. So again, it's basically saying the same thing. If it can't carry the loads, if you're in a collapse situation before you put the FRP on, you should not be using FRP, because there's no way to fire protect FRP. You can maintain fire ratings and use FRP, but you can't actually fire protect the FRP. It's going to burn and be lost generally in about 10 to 15 minutes in the event of a fire. So both the CSA and the ACI guidelines address that and prevent you from using FRP in situations where it would be required as a primary load carrying member. So we'll go through now some of the applications and kind of some of the engineering associated with that. So if you imagine a beam or a slab, we can do a flexural strengthening for positive bending on the underside. So as you imagine, we've got just a gravity load. This could be a beam, a slab, whatever, it's going to bend. So we're just putting the material on the bottom side. That's very important. The material always has to be placed on the tensile face of the concrete. It can't be placed on the top in this situation because that's the area of the beam or slab that would be in compression. With FRP materials, they're only able to assist in tension. They don't provide any compressive capacity with the exception of a column, which is obviously different because you're putting the material in the tension. But in this case, you'd be actually compressing the fabric. And if you just take a piece of paper and crumple it up, obviously there's no resistance when you do that. FRP is exactly the same. So the material always has to go on the tensile face of whatever member you're strengthening. So when we do negative moment strengthening over the supports in this example, then the material does have to go on the top because that's our tensile face. So with the cantilevered member, the material would need to be on the top, obviously. Whatever the tensile face, tensile zone of the member you're strengthening is, that's where the material needs to be placed. In a situation like a moment reversal, like if you had a blast down below, or ever in the projects where you had a cantilevered slab that was deflecting, so they decided to shore it up permanently with a column and then turn it into a simply supported member. Well, now you're reversing. So again, you have to always make sure that you get that material placed on the tensile face of the concrete. Question comes up a lot, the contractors especially, if they're on a job site and there's, that you specified that it goes on the underside because that's where it needs to be, but they see all the, the HVAC pipes and ducts and everything else, and they think to themselves, geez, it'd be a lot simpler if I could just put this on the top. So they'll ask the question. Unfortunately, the answer is no. They have to get around those obstructions because the material is not going to provide any benefit when you place it in the compression zone. Works the same way for walls as well. Again, tensile face. So if you've got bending of a wall, this is a simply supported wall, so it's going to go on the opposite face of the loading. If you have a retaining wall with maybe a soil load on the one side, then you do have to put it on the face where the bending is expected to occur. So if you have a retaining wall situation, yes, that does involve having to dig out around the wall and place the FRP and then backfill afterwards. So again, very, very important that we know where the tensile face is, where that will be, and that's where the material has to go. So just kind of some general rules of thumb as it pertains to the flexural strengthening. We can do it for really any type of concrete, lightweight concrete, traditionally reinforced concrete, post-tension concrete, pre-stressed. It doesn't matter. If it's concrete, we can strengthen it. There are some differences in how we approach the actual design of the FRP when we're looking at, say, a post-tension system versus just traditionally reinforced. There's some different design equations in the CSA and ACI guidelines, but you can still do it. If you get into any kind of moment redistribution, I know ACI allows that. I would assume CSA also does. I'm not super familiar with CSA's building codes, but I would presume they also allow that. There are some limitations on moment redistribution when you're using FRP. It used to state that the effects of FRP weren't known, just proceed with caution, which was kind of a waste. I mean, it kind of flagged it, but said we can't help you with how to handle it. Fortunately, they've changed that now, at least in the ACI 440 document, and they give you specific equations on how to reduce the amount of moment redistribution that you can take advantage of when you do use FRP. So it's certainly something to pay attention to if you are doing some FRP strengthening, but also using moment redistribution to try and reduce the amount of strengthening that you need. You do need to pay attention to how that allowable moment redistribution gets reduced by using FRP. The third point there, this question comes up a lot, and that's that the material just does not effectively reduce deflection. So, you know, we'll get a call, an engineer will call and say, hey, I got this beam, it's deflecting, you know, 4 inches, which is obviously pretty excessive. You know, we wanted to get it to 2 inches. Can we shore it up, put the FRP on, and then pull the shoring, and then stop that 4-inch deflection? Unfortunately, no. If it was deflecting 4 inches before, it's going to probably deflect, you know, 3.8 or 3.9 inches. So it really does not affect deflection at all. And the reason for that, it's just not stiff, not nearly stiff enough to actually reduce deflections. You'd have to, you know, do a steel plate or something that's much more stiff than the FRP. As far as a rule of thumb, if you're kind of looking at a project and you got to do some strengthening, you know, and you want to just kind of get a rough idea, well, is FRP possible? The first thing you'd have to do is check those equations that I showed previously to make sure that you can carry the service load without the FRP. Assuming that you can, we can generally increase the FRP, or I'm sorry, increase the strength of the existing member by about 70% in bending capacity. It's not a hard number. It might be a little bit less. Sometimes it's a little bit more, but it's kind of a general rule of thumb at, you know, 70% is kind of our ceiling. So if you're looking at a beam and you're trying to triple the bending capacity, we could tell you right off the bat, there's just no way that FRP is going to be able to get you there. If it's 65 or 75%, then yeah, we you know, it's going to probably take a lot of material, but we can probably most likely do it. So it's just kind of a general rule to help you along, you know, on a preliminary basis to see if FRP might be a possibility. Real quick here, the only thing I want to point out here, if you look at this equation on the bottom, if you were to just look at the left-hand side, the A sub S, F sub S, and then the neutral axis location. If you're designing concrete, that's the equation you use. You get the area of the reinforcing steel times the stress of the reinforcing steel times the neutral axis location gives you the bending capacity of that member. FRP is really designed in the exact same way, except we have the area of the FRP as opposed to the area of the steel. Then we have the effective stress in the FRP as opposed to the stress of the steel. And then we have the neutral axis location of the FRP as opposed to the neutral axis location of the steel. So it's really no different than what you're used to doing. It's just different materials and different material properties. Now, as far as where, you know, that 70%, why is there a limit? Why can't we just continue to put more material on and get more strength? The reason is, and I mentioned this before, is that we can't ever get to the ultimate strain or stress of the material. It's going to delaminate at some point prior to that. So the way that the guidelines handle this is they've come up with this debonding strain or effective strain that gets calculated based on these equations here. They're the same in CSA and ACI. The only difference is for the metric units or for the US customary units. But you can see here, it really depends on the strength of the concrete, F prime C, the compressive strength of the concrete. And then on the bottom, you've got N is the number of layers of material, then the stiffness times the thickness of that material. So as we increase the number of layers, this allowable strain starts to converge on 0. Generally, with your standard 600 grams per square meter, that's the 18 ounce per square yard material. Around 3 or 4 layers, you start to get to that 0 strain. So adding 5, 6, 7 layers, well, it's going to add a very, very small amount of additional capacity. It's really negligible. So it doesn't make sense to spend that money and just keep dumping, adding more and more layers to get essentially no return. So that's where that upper limit comes from, and that's to prevent the material from delaminating due to overstress. So that's where that upper bound comes from, as far as 3, 4 layers or the 70% kind of max for flexural capacity. For shear strengthening, there's either in plane or out of plane shear strengthening. The material can be used for both. Which direction you run it obviously is going to depend a little bit on what's the direction of the shear being placed on the wall. There's different requirements as far as the thickness of the wall. So I think it's like 4 4-inch walls and 6-inch wide walls, you can get away with putting the material on just one side of the wall. If it's 8 inches or wider, then you have to actually put the material on both sides of the wall. So there's that all comes straight from the ACI guidelines. I'm sure probably there's a similar requirement in the CSA as well, as far as which sides you need to place it on. But generally anything 8 inches or wider, you're going to need, which I believe is 200 millimeters, you need material on both sides. If you have any overturning going on, if you need like force transfer into the to the slabs to help tie everything together, you can do that with a steel angle bonded to the FRP, and then you would anchor that angle down into the concrete. This would be a great example when I was talking earlier about the conductivity of the carbon and having to pay attention to that. This is a prime example of that. So in this case, we would want to either put a piece of fiberglass in between the carbon and the steel angle, or just make sure that we put in a lot of extra epoxy to make sure that there's no contact between that carbon and that steel, so we don't get a corrosion cell starting and then corroding the steel plate that you're relying on. So good example of that. Shear strengthening of beams. Typically we use what we call a U wrap because it's shaped just like a U, pretty self-explanatory. You can also do just on the sides, or you can wrap all the way around. There's varying effects. If you can wrap all the way around the member, you get the biggest return, the largest increase in capacity. But obviously you can't often do that because there's a slab or something. You know, we generally don't just build beams for the look of the beam. Sometimes the architects do that, but you know, not very often. So usually you can't wrap all the way around it, so that's why we do the U wrap. But then there's instances where maybe there's a steel plate that's been already installed on the bottom, or you've got obstructions of some kind and you just can't wrap underneath and around. So in that case, you actually can just put the material on the sides only, but you do get a further reduction in the capacity provided when you do that. But it is a possibility. So if you have an obstruction, you know, don't just say, oh, I can't use FRP because I can't get a U wrap. That's not the case. It's just you get a reduction in capacity provided by the FRP. So again, similar to Flexural, I mean, any type of concrete is fine. Beams, walls, shear diaphragms, if you're in a seismic region, FRP is great for that. There are some really good guidelines in both the CSA and the ACI for seismic applications. You can expect generally about 2 kips per inch of beam depth or wall depth as far as how much capacity you can get, which is 3.5 kilonewtons per millimeter for our Canadian friends. So a 30-inch deep beam, you can figure, you know, about 60 kips of shear capacity that you'd be able to get. Is just kind of, again, it's not a hard fixed number, but it's just a rough approximation if you're kind of on the preliminary stages of a project and just trying to explore your different options. You know, if it's 30 inches deep and you're trying to add 200 kips, there's just, you know, again, because of that delamination equation, the delamination strain, there's just no way we could get there. And then lastly, FRP systems are not effective for punching shear. So if you have a punching shear issue, anyone that's not familiar with that, it's if you have a column being supported on the slab, a supported slab, the column, because of that concentrated load, it wants to punch through the slab. So if, you know, they will put a thick, what we call a drop panel or a thickened area of the slab underneath where the column is. But you know, if it's an older building and they, you know, they didn't really understand the principles as much when it was built, there might not be a drop panel. So you might have punching shear where the column's punching through. Unfortunately, FRP is not effective as a solution to that. Then the third kind of main application we'll see is just column confinement. So that's just wrapping around the column like we see here. So really you get a marginal increase in axial capacity of that column, but you really get significant gains in ductility of the column, which is why it's so great for seismic strengthening. the equations from both the CSA and the ACI are very similar, just a little bit different factors for the CSA versus the ACI. But the way you do it is you calculate a confining pressure that the FRP provides by wrapping around it. And then you use that pressure to calculate the additional compressive strength that you're providing. Now, it's not much. You know, on a round column, you're going to get somewhere probably around like 100 psi, anywhere from 50 to 100 psi of additional capacity per layer, which is not much. You know, so if you've got a column with, you know, you're looking to get like on you know, additional, if you're tripling or something, you're adding a ton of weight, you're probably not going to get there with FRP. The difference with columns versus flexural or shear, it is not what we call bond critical. So there is no delamination concern. So you can actually use 100 or 200 layers of FRP. So in theory, you could get any load you wanted to, but it's going to be way too expensive when you start talking about that many numbers of layers. So you know, it's really not, while you can get, you know, some increase, it's not the best way of adding compressive capacity to the column. There's certainly other ways that'll get you more. It's really that ductility enhancement that we get out of the FRP. And then another thing a lot of the DOTs are doing, as I mentioned before, is they're just wrapping. If you got a lot of, you know, up in the north where we're dropping snow, salt everywhere for the snow and the ice, you get a lot of just deteriorated columns from the plows going by and blasting them with all the snow and the salt. So you get a lot of spalling and cracking. The DOTs are using it just as a layer. They'll throw a layer or two of glass around the column, just not really for any load carrying capacity, just as a help hold it together and maybe extend the service life of the column out a little bit longer. Here's a you know, in practice view of that. This is a double column, so you can see there's a column and then another column immediately adjacent to it. There's probably only, I don't know, maybe an inch or two in between those columns, which would be about 50 millimeters or so between, which is really all the room you need to be able to actually install the FRP. If you can fit a paint roller in the space, you've got enough room to install a system. So really, really versatile material as far as the installation side that Hamza is going to get to here in a second. You can do confinement for square columns. Obviously, we're showing one here. There are limits to that. I'm not sure what the CSA is, probably similar, but in the ACI, the limit is the side aspect ratio has to be less than 2, which means no one side can be more than 2 times larger than the other side. So if you had say a 36-inch by 12-inch column, you can't confine that with FRP. You'd be limited to a 24 by 12, or if it was 36, the other one would have to be 18 inches. You know, pretty simple math. And then no face can be larger than 36 inches. So if it's a, you know, a 4 by 4 foot square column, that's actually too large to wrap or to confine with FRP. You're limited to a 3 foot. Now with a round like pipe or a really large column, it can be as large as you want. I mean, we've wrapped tanks that are probably 200 feet in diameter. But this is just, the limitations only apply to square or rectangular columns. Then we've just got slab openings. I talked about this at the beginning, where you know, maybe you're cutting a hole in the slab, you cut some steel. We're just replacing that cut steel with the FRP. It also helps control cracking at the corners there. So oftentimes, even though the bars are just running in one direction here, we would actually run material perpendicular to the bars also, just to help control cracking at that re-entrant corner. It's certainly a good idea to do that. But again, the material needs to be placed on whichever side the bar was. So I showed top bars here. So if we cut a top bar, we need to replace the material on the top of the slab. If it was a bottom bar, we'd want to replace that, place the material on the bottom of the slab or the beam, whatever it may be. All right, so I will hand it off to Hamza then. He's going to take you through the installation.
Perfect. Thank you, Brian. Always a pleasure to hear you sharing your knowledge about FRP. So my part of the presentation consists of detailing and illustrating key steps of FRP systems installation. We will see together for probably 10 to 12 minutes, preliminary steps prior to application, surface preparation requirement, application of products of each system, and some quality control hints. So before installing the selected FRP system, all unsound concrete must be removed and repaired per ICRI guidelines using appropriate concrete repair material and methods. If there was corroded steel rebars, it is highly suggested to expose them, clean them, and protect them against future corrosion using appropriate solutions such as galvanic anodes or corrosion inhibiting coatings like the blue one we see in the middle picture. Once repair material is applied, adequate time must be provided for the repair to fully cure. Next slide, please. The existing concrete must achieve a minimum concrete surface profile of CSP3 per ICRI. The CSP3 actually will ensure that the pore structure of the existing substrate is sufficiently open to ensure adhesive bond between the substrate and the FRP system, which is essential for bond critical applications such as flexural strengthening. Next slide. You can consult ICRI guideline number 310 for acceptable methods to achieve the desired surface profile. One of the most used ones for vertical and overhead applications is sandblasting to CSP3. As you can see in the pictures in your right, sandblasted concrete showed open pores and made many cracks evident. Next slide. If the FRP fabric is to wrap around any corners, a smooth transition must be created and provided to avoid concentration of stress. The minimum radius accepted is a 3/4 inch, so about 19 to 20 millimeters, but the design engineer may have to increase the radius for heavier fabrics such as the 1200 grams per square meter. Next slide. Due to thermal and or structural movement, existing cracks may open and close over time, which may cause buckling of our FRP system. So all cracks greater than 0.3 millimeters, so around 10 mils, must be epoxy injected. Next slide. The cracks could be either injected under pressure or filled with epoxy by gravity feed, as we can see in the picture in your right. Next slide. The FRP system must only be installed under the appropriate environmental conditions. So first, ensure that the expected temperature range falls within the acceptable installation tolerance for each epoxy component. Typically, the range is between 5 to 32 Celsius degrees, so between 40 to 90 Fahrenheit. Second, the FRP system must be installed on a dry substrate. So be sure that the surface pores of the substrate are not saturated with water or moisture prior to installation. For that, you can measure the moisture content using ASTM F2659. If the result is under 4%, you're good to go. If it's above 4%, you have to consult the manufacturer or try to work something with the engineer of record to fix that. You also have to identify and address any source of potential leaks that could allow the accumulation of moisture behind the installed FRP system, as this may lead to delaminations or blistering. Also note that the temperature of substrate must be superior to the dew point by 3 Celsius degrees. This step is actually a critical checkup to do, especially for exterior applications. Next slide. Now let's go through application steps of FRP systems, starting with FRP fabrics. So the FRP fabric system looks like this. We first have the primer to consolidate and seal the surface of the prepared concrete. Then you can use the epoxy putty to level the surface. And then we have the FRP fabric impregnated with the appropriate saturating epoxy. And then if you want to hide or protect your FRP system, you can sand broadcast and apply a top coat or another material on top. Due to the fast setting nature of the epoxy materials involved in the FRP system, the fabric should be prepared prior to mixing the epoxy components. So the contractor has to cut the strips to the required or designed length and width using a sharp tool. Also keep fabric clean of dirt and contaminants, and always avoid folding or creasing the fabric. Next slide. When mixing the epoxy components, try always to add the part B to the part A. Mix for at least 3 minutes using a low-speed mixer, and use ideally Jiffy style mixing paddle for most of the epoxies. Next slide. Also select the appropriate tool for each component to apply it. So for example, the primer, which is very fluid, can be applied using a paint roller, and the epoxy putty, which is much thicker, will require a trowel or a spatula. Coverage rates obviously are provided on each relevant technical data sheet. Next slide. So here is a summary of FRP fabric installation procedure using the dry layup method. We will see another method in few seconds. So the first step is to apply the primer component. You can see the primer in the brownish zones in the pictures. Second step is to apply the putty component to level all the surface or only irregular surfaces, as you can see in the two pictures. The third step is to apply the first coat of the saturating component, then place the FRP fabric into the still weight base coat of saturant. After that, you can roll the FRP fabric to remove wrinkles and achieve a tight installation, and finally apply a second and final top coat of the saturating epoxy component. The wet layup method is slightly different. In the wet layup method, the saturating machine is used to pre-wet the fabric prior to placement. The purpose is a full impregnation of heavy fabrics fibers using a low viscosity epoxy, but the technique could also be used for regular fabrics. The FRP fabric is actually rolled through a basin filled with the saturating component, and the rollers ensure complete saturation of the fabric while removing excess of epoxy. The pre-wet fabric is then placed on the substrate and rolled tight using drum rollers. Next slide, please. Obviously, the substrate must already have been properly prepared, and the primer and putty components must be applied prior to commencing fabric placement using the wet layup method. In this job, the contractor preferred using the wet layup method instead of the dry layup because he felt more productive with the wet layup, even if he had the choice actually to use the dry layup method. Next slide. If the FRP system is exposed to UV, a top coat must be applied to protect the system. It may also be required indoors for aesthetical purposes, so the engineer will reinforce his column and the architect will want to hide it with the acrylic paint or something like this, so we can hide the structural intervention. For that, the contractor has to broadcast send to refusal into the final top coat application of the saturating component and allow to reach a tag-free state before applying the top coat material. Next slide. In this bridge, FRP intervention was protected against UV using a special acrylic coating, and the public can barely notice the intervention. Next slide. For the FRP procured laminate installation or the CFRP plates, the surface preparation requirements remain the same as fabric applications. Then we still have to prime the substrate as recommended by the manufacturer. Then remove the peel ply from the side of the laminate to receive the epoxy, and apply a uniform layer of the epoxy adhesive to one side of the laminate. Next slide. Also add a layer of epoxy putty on concrete substrate, then press firmly against the substrate to achieve bond using rubber rollers or equivalent hard tool. Next slide. To inspect and check the quality of installation, the most famous tests are tap test and pull-off test. So the tap test is quite simple. Using a hammer, lightly tap the installed FRP system while listening for void spots. During the training, the manufacturers put a lot of emphasis on avoiding voids for the plates and bubbles for the wraps. For the pull-off testing, a number of pull-off tests can be completed following application of the FRP system. So using the right tool or the right machine, a minimum tensile pull-off strength of 200 psi, 1.4 MPa must be achieved to be considered a successful installation. Failure should occur in the concrete for a pass test. In the next two slides, we will see two different projects where pull-off test was used for bond critical applications. So in the Champlain Bridge, FRP fabrics were used for shear strengthening. The large amount of fabrics involved in this project obliged the engineers to plan independent and dedicated zones for pull-off tests. Next slide. In Place des Arts, downtown Montreal, procured CFRP laminates were used for flexural strengthening to increase negative resisting moment. In this case, contractor and engineer agreed on installing extra length of some plates compared to their design length and conducted pull-off tests on them. Failure always occurred in concrete, and results were between 2.8 MPa and 4 MPa, which is about 580 psi, which is way above the minimum required of 200 psi or 1.4 MPa. That's it for me. Thank you for your attention. I will leave it to Brian to conclude our presentation.
Okay, thanks, Hamza. Yeah, just in closing, really, I just wanted to introduce some of the guidelines that are available. So here in the U.S., we use the ACI 440.2R. That's 2017 is the most current version of that. Then there's a whole host of other 440 documents. Most applicable for most of you from a design standpoint, really just the material specification, the .8-13, but there's documents on FRP pre-stressing, FRP formwork, all the various tests that need to be run. There's all sorts of documents, but the 2R17 is really the main design guide, and then the .8-13 is the material specification. In Canada, they have the CSA S6 as their bridge code, that it does include sections on FRP. And then they have a separate, the S806 is the code for buildings, specifically FRP, either for, and I believe in Canada, they allow it to be used for new construction as well. So that document has guidelines for using FRP in new construction and then also repair as well. And then they have the S807, which is their specification for FRP materials. So definitely worth your time to grab a copy of those documents if you're going to be doing any kind of FRP design on your own, with your own firms. So that concludes the AIA portion of the presentation. We're going to take questions in just a second here, but kind of outside of the AIA, I just wanted to real quickly let you know what we at Mapei are able to provide you as far as FRP support goes. So we do design calculations either using MathCAD or Microsoft Excel. We can do detailing and shop drawings, like you see in the top picture there. Is just kind of an example drawing that you might get. But we're also available for any kind of seminars like we're doing today, lunch and learns, those types of activities, and then applicator trainings as well. So most of the specifications will typically require that the contractor has been trained on the system they're installing. So if we are required to provide that training, we're certainly more than happy to do that. We do all this at no charge. This is just a service we offer. So if you have a project and you need some help, getting some drawings put together or calculating how much material you might need, or you just want some help with a specification, whatever it might be, feel free to call your local Mapei representative, and we'll certainly be happy to help you out with that. So with that said, here's just a few additional references. ACI, obviously, I mentioned. ASCE has the Journal of Composites and Construction. Then ICRI has a guide specification for FRP. We're currently working on a inspector certification program through ICRI, where inspectors, building inspectors, could get certified to be a FRP installer. So it's kind of some of the things we can look forward to seeing here in the near future. But with that, if anyone has any questions, I think Jen is probably going to be reading them to us.
Yep, there are a few questions. We're a little bit over time, so we'll take a few, and then we'll send the rest over to Mapei digital@mapei.com. But the first question is, can FRP be used to strengthen heavy timber beams for increased flexural capacity?
So the simple answer is yes. The more complicated answer to that is kind of a maybe. The issue with timber, while FRP is an acceptable means of strengthening timber beams, there's the first problem is there's no design guidelines specific to it. So typically we just look at it as, okay, well, we're going to provide this much additional tensile capacity to the material. One of the kind of issues with timber is that it's like steel. It's more of a balanced situation where you have a equal parts compression and tension. Whereas in concrete, that's not the case. You have much lower tensile capacity from the concrete, and you use the steel. So it's a little different with timber, where when you add tensile capacity, you almost have to really match that with the additional compressive demand that's going to place on the member. So it gets a little tricky, but most of the time, yes. The answer is yes, we can do it. It's just one of those things where we have to look at on an individual project basis to just determine if it is in fact okay for that specific application.
Cool. All right. The next one, can FRP cross steel with a 1 millimeter thick epoxy paste between the two products?
Yeah, I think probably a millimeter would be sufficient. You just got to make sure that there's zero contact between the FRP and the steel. The epoxies are not very expensive, so I mean, unless you had an issue where you really had to control the thickness, I wouldn't worry so much about trying to use as little as possible because it's pretty cheap. But if you do have a thickness concern, then yeah, I mean, one millimeter should be sufficient as long as it's continuous and there's no exposed steel touching the exposed carbon.
Okay, good question. Here's one. If a pull test is done and it fails at 2.7 MPa, but fails at the epoxy bond to the dolly, is this a fail? And if so, why?
Yeah, so it's a good question. Actually, we had a situation, I think, in Ontario with my colleagues in Ontario, where the failure always occurred on the in the epoxy glue used to bond the dollies. And yeah, the engineer accepted the pull-off test because it tested above 1.4 MPa, so it was an acceptable result.
Right.
Nice.
Yep. It's the only thing you're looking for is to exceed the MPa or two. I'm not sure what the MPa version, but it's 200 psi is the minimum for ACI. So yeah, anything over that, once you get over that, you're passed. It doesn't matter how it fails at that point. They're just looking for that minimum of whatever that minimum is. So beyond that, yes, it is considered a passed test.
Cool. Okay, bear with me. This is a long one. When we have a damaged structure, i.e. a double T steam in shear, do you provide services to check the existing capacity of that member, or an engineer would have to check that for you before hiring you for the strengthening design or application?
Right. So we do not provide any engineering services as far as the existing structures. We're not a consulting engineering firm, and to be honest, we don't even stamp. While we provide designs for the FRP, we don't stamp them. So we get third-party engineers involved if they need to be stamped. So in the situation described in the question where there's some sort of shear issue, yes, a consulting engineer would need to be hired to determine what amount of strengthening is required. Where we are able to help is, and once we know how much shear capacity is required, then we can design our system to provide that amount of shear capacity. But we're not able to do any analysis of existing structures to determine deficiencies. That's up to the engineer of record, or if it's just an owner or a contractor, then in that case, they would have to hire an engineer specifically to do that.
Yeah, good question. All right. Well, as I said before, we are a little bit over time, and we don't want to take up everybody's time because we do know it's very precious, and we appreciate them listening in today. If there are any more questions, if you're thinking about it during the rest of the day, please send them to mapeidigital@mapei.com, and we'll be sure to get them to Brian and Hamza or the appropriate rep. And we really thank you for spending time with us today. Brian, Hamza, thank you for this presentation. It was great. It was really informative. And we look forward to seeing you guys again. And we'll see everybody at the next webinar.
Thank you very much.
Thank you. Have a good day, everybody.
Thank you.
Bye.